All right, time to attempt to do more physics. Do or do not. There is no try. That's what Yoda said. Let's see, what are we doing here? 8, 12, and 15 through 18. Let's see how it goes. Let's see how it plays out. Number 8. We got a plane flying 483 kilometers east from city A to B. And then, in 45 minutes. That's 3/4 of an hour. And then 966 kilometers south from B to C. In 1.5 hours. For the total trip, what's magnitude and direction of the plane's displacement and the average velocity and its average speed? All right, so let's see. The displacement is this vector from here to here. So for its displacement vector, we might as well call that the origin. It doesn't matter where you move this around to, the displacement must be the same. So I'm just going to go ahead and call that 483I minus 966J kilometers. And they want the magnitude and the direction of that. So my batteries are still low in case you're keeping score there. So let's Pythagorize 483 squared plus 966 squared. That's about 1,080 kilometers. That's the length of this, right? That's the magnitude of its displacement. And then that angle, tangent inverse 966 over 483 is about 63 degrees. And this is a north, south, east, west situation, so I'm going to say that that is south of east. I believe that's the answers for A and B. That's what they're asking there. Yep, the book, you don't need to know what the book answers are because these are even, so never mind. Forget I said anything. Then let's see, we want for B and C, average velocity. So average velocity is displacement over time. Now that's just this divided by the time. Now if I have this already in this form, dividing by time is, I can just divide the magnitude by time, and of course how much time it takes doesn't change the direction. So I'm going to go ahead and divide that by, what do I have, 2¼ hours. So 1080 divided by 2.25, that is 480 kilometers per hour, and the direction is the same. And how about the average speed? Well, the average speed, which sometimes is just written as v without the vector hat. I know that's potentially confusing, but if it's not a vector, well, I guess that must be the speed, the magnitude of that. That is equal to the total distance divided by time. So the total distance is this plus this. Which is 664 kilometers per hour. And there's no part F where they ask for the direction of this because that's speed. It's not a vector. It doesn't have direction. I think that's everything for 8. Yeah. Number 10. Are we doing number 10? Nope, just kidding. Number 12. At one instant, a bicyclist is 40 meters due east of a park's flagpole. Shall we make the flagpole the origin? I don't know. Let's keep reading. So they're 40 meters due east of a park's flagpole, going due south. With a speed of 10 meters per second. And 30 seconds later, the cyclist is 40 meters north of the flagpole, going due east with a speed of 10 meters per second. So I suppose you could imagine that they're riding in circles around the flagpole. You ever play that game? When you're little? With your little buddies? Hey guys, you guys want to play Let's Ride in Circles Around the Flagpole? So for the cyclist in the 30-second time interval, what are the magnitude and direction of the displacement, the magnitude and the direction of the average velocity, and the magnitude and the direction of the average acceleration? All right. Well, the magnitude of the displacement I'm always going to start with component form. So this is where we started. This is like my initial position, and this is my final position. Oops. Started making an F when I was making that R. So those, if I want to do this minus this, it doesn't matter what you consider to be the origin. The vector that points from your initial position to your final position, if you can write that in component form, that's what we're looking for. So from here to here, from this initial to final, the displacement is negative 40I plus 40J. It's like directions, right? You go 40 this way, and then you go to that. That's how you get from here to here. And this is meters, right? So I think for parts A and B, we want the magnitude and the direction of that. So let's Pythagorize that. Of course, that's just 40 square roots of 2. That's like a special right triangle. So-called special. Maybe you thought all along, you're like, what's so special about that? All right triangles are kind of special because of the right angle there. B, the direction, that is going to be, this is a north, south, east, west, so I'm going to call that 45 degrees north of west. Right, it's pointed in this direction from here to here. All right, how about the average velocity? Well, I have the displacement, so I just have to divide that by time. And my time is, what is it, 30 seconds? Right? So dividing those, that's negative 1.33 plus 1.33 J meters per second. And I can Pythagorize that, or just multiply by the square root of 2. That's 1.9 meters per second. And the direction of the displacement and the direction of the average velocity are not ever going to be different. And that is impossible. Let's see where we are at here. And then we want the average acceleration. I'll leave myself just a wee bit more room here. I think in the first batch of problems that you did from this part of Chapter 4, early Chapter 4, you didn't have any average acceleration problems. So I'm just going to make sure that we understand how to do this. Sometimes I ask questions about this, or that have to do with this, on the Chapter 4 test, and students don't seem to know what the heck they're doing. So make sure that we know how to do this with our vectors. Now, what does this mean? That means your final velocity minus your initial velocity, but those are vectors, so I think I would like to have them both in component form, right? So my final velocity is this here. So that's 10 meters per second in the positive I direction. 10I plus 0j, just for emphasis there, meters per second. And my initial velocity is, there's no I component, minus 10j, meters per second. So when I subtract those, here, 10 minus 0, that's 10I, 0 minus negative 10 plus 10j. That's the difference in velocities there, so that would be in meters per second. Over the time interval, which is 30 seconds. Now, you might be looking at this and going, okay, this is weird, because this is a vector. This velocity vector is pointing like this way, right? It's got positive 10 as the components, an I and a j. So what does that have to do with this, the cyclist? Well, what it has to do with this is if you want to change your velocity from this to this, that is what you need to do to it, right? The acceleration or change in velocity needs to be this way. Why does it need to be this way? Because part of it has to, if we're going to get to this, like all I direction, then part of the change has to be, you got to wipe this out, right? You got to get rid of minus negative 10. You have to get rid of this down part, so you're going to need an up part there, right? And then, well, this doesn't have any I component, so that has to come from somewhere, so it must also have this part. So that's the change that has to happen to get from a velocity of this to this. And yeah, it's all basic mathematics. So we would like to know what this is in magnitude and direction form. So here, the magnitude of this is 10 square roots of 2. I think that's about 1.14, isn't it? Square root of 2. Oh, yes. So that's 14 meters per second divided by 30 seconds, divided by 30. That's 0.47 meters per second squared. And the angle of it, you can Pythagorize these, or you can divide them by 30 and then Pythagorize them. It's the same as, like, the angles of these aren't going to be different because they will proportionately be the same relative to each other. So let's see, 10 and 10, that is 45 degrees north of east. That is how you do that. Right. Paying special attention to that. How about number 15? I think that's next. Number 15. We have a particle leaves the origin with an initial velocity of 3I meters per second and a constant acceleration. I don't have to put an I there. This is its constant acceleration, so it's not changing. Minus 1I minus a half a j meters per second squared. When it reaches its maximum x-coordinate, what are its velocity and position vector? Ooh, when it reaches its maximum x-coordinate, how do we figure out when it reaches its maximum x-coordinate? Well, we do know that it's at the origin, so its initial position is 0I plus 0j meters. And we want to know when it reaches its maximum x-coordinate. Well, there's a couple ways to think about this. I think at this point, what we would like to do is consider here what this acceleration is going to be doing to this velocity. So let's have a little meditation here on what exactly acceleration is. Acceleration is what happens to velocity. It's the rate that the velocity is changing at. So here, I'm going to make a little table here. Time 0, and say this is the velocity. I guess I didn't need that extra column here. Well, maybe you do. I think I want to separate here. This is like the x component of the velocity, and this is the y component of the velocity. So right now, at time 0, the initial velocity is 3I. So its x component is 3, and its y component, it doesn't have one. Right? Now, what about at time 1? Well, the acceleration tells us what's happening to the velocity every second, and it's a constant acceleration, so it's really easy to deal with, right? This tells us right here that every second that ticks by, we're going to subtract 1 from the horizontal velocity. That is not a hard pattern to execute or understand. And every second that goes by, we're going to subtract a half from the y velocity. Etc. Okay, so that kind of gives us an idea what's happening here. And we might note here, if we think about the path that this thing is following, then at time 0, its velocity is 3, all to the right. If you're thinking about the positive I direction, is to the right. And then after that, it's got, it doesn't have as much velocity here. It's got a little bit of negative. So after it does this, then it's going to be, it's like bending down this way, right, a little bit, because this is not as big, and that's a little bigger. And then a little bit later, now it's like 1, -1, so it's headed this way. Remember, the direction of this is also the direction of travel. And then here, there's no component here anymore. It's only this down, and then that starts to come back this way, and so on. So let's think about these questions they're asking us about this. A particle leaves the origin when it reaches its maximum x-coordinate. When does it reach its maximum x-coordinate? Well, if you look at the x part of what's going on here, it's going in the positive direction here until it has a velocity of 0 in the x direction, and now it's going negative. So this right here, this is the turnaround. So it's going in the positive direction, and now it's going in the negative direction. So its maximum x-coordinate is going to happen at time 3. That is when that happens, because that's how long it takes for this acceleration in the x direction to knock this down to 0, and then after that, it's going to change its direction. So we know the when, that happens at time 3. They didn't actually ask that, although we do need to know that. They want to know what are the velocity and position vectors. Well, the velocity vector is this. We have that right in our table there. The velocity vector at time 3 is 0, I, minus 1.5 j meters per second. Now how about for B? How shall we do that? Well, these are constant accelerations, so we can treat both of these like little constant acceleration problems separately. So in the x direction, I've got a constant acceleration of -1. I've got an initial velocity of 3. 3 seconds are going to go by, and I would like to know where it is. Right? I can do this because this is a constant acceleration in the x direction, just looking at the x direction. And let's see, this looks like a delta x equals 1/2 at squared plus vit situation. Those are both 3. That confused me for a second. Right? So let's see, that's going to be 9 minus half of a 9, so that's 4.5 meters. So that is the position. If we're looking for what's the position at time 3, then 4.5 I is going to be the horizontal component, and then to find the vertical component, I'm going to do the same thing. But in the y direction, the acceleration is negative 0.5, constant. The initial velocity in the y direction is 0. Time is still 3. And I'd like to know this delta y. So same deal, delta y is equal to 1/2 a t squared, and then plus vit, that's 0. So I can leave that off. So it looks like I have half of a negative 9, so I believe that that is minus 2.25 j meters. So that's where it is. And that's how you do that. You got to recognize that we are allowed to use our kinematics equations because we have constant acceleration. See if I can tuck 16 into this space here. The velocity v of a particle moving in the xy plane is given by this. With velocity in meters per second, time greater than 0 in seconds. What's the acceleration when time is 3? When, if ever, is the acceleration 0? When is the velocity 0? And when, if ever, does the speed equal 10? The speed equal 10. All right, so let's see. First question is, what is the acceleration when time is 3? If this is the velocity, then the acceleration is the derivative of that, 6 minus 8t, and then derivative of 8 is 0, so it's just that. If you wanted to really drive that point home, you could put that there. So for part A, the acceleration at time 3 is, plugging 3 in here, 6 minus 24 is minus 18 I meters per second squared. All right. How about for part B? What are we doing? Part B, when, if ever, is the acceleration equal to 0? If you say when is the acceleration equal to 0, that's only going to happen when both components are equal to 0. So this is always 0. I don't have to worry about that. And this is 0 when t is 3/4, right? Just doing a little bit of math there. At t equals 0.75 seconds. Now it's possible that it could never be equal to 0 because these things have to both be 0 at the same time. It's not enough for one or the other to be 0. In this case, that's always 0. So we did find a time there. Let's see, part C. When, if ever, is the velocity 0? All right, so let's see. For the velocity to be 0, both components would have to be 0, and this one's 8, constant, so that can't happen. So never, because the y component is never 0. Not happening. And part D, when, if ever, does the speed equal 10? This is a little bit trickier. So how do you find the speed? Well, speed is the magnitude of velocity. So speed is like the Pythagorized velocity. If you have the components of the velocity and you want to know the speed, well, you got to find the Pythagorized components, because the speed is the magnitude of this vector. These are the two legs, the two components, and speed is the magnitude of it, how long it is. So if you want the speed to be equal to 10, that means the Pythagorized these has to equal 10. So that's 6t minus 4t squared plus 8 squared. Square root of that must be equal to 10. So I don't know, you got to do some math now, right? There's ways of doing graphing stuff with your calculator. There's really super intuitive ways of realizing, wait a second, if I want this hypotenuse to have a magnitude of 10, and this is 8, this must be a 6, 8, 10 right triangle. That would be clever. Or you can just do algebra and square both sides of this. 6t minus 4t squared is equal to, that's 64, subtract that over here, 36, and then this is the point where you arrive at that intuition. Anyway, take the square root of both of those, and then what do we have here? We have getting everything on one side, algebra is happening, and dividing by 2. Looks like I would have 2, moving this over here, 2t squared minus 3t plus 3. And does that factor? Oh boy, I don't think so. So if that doesn't factor, you can, that's pretty quadratic formulatable. Or, since this is physics class and I'm allowed to use my calculator all the time, I might as well practice those skills. So I could do that, and then see, my window is 0 to 2. Is that where it's going to cross? I don't know. I don't think I like that. It's not going to be in any negative times anyway, so how about 0 to 10? And then I just need to see where that crosses. So how about that? And, oh, I think I know what, let's see. This, I took the square root of both sides of this. This is getting squared. So this thing, for this to equal 36, this could equal plus or minus 6. So there's another version of this. That's a little tricky there, huh? 2t squared minus 3t minus 3. So could also be that. That's tricky. There it is. Looks like it crosses between 2 and 3, so I'm going to do this. I'm going to find the 0. I hate the cursor game. I'm just going to type in, I know it's between 2 and 3. 2.2. All right. Number 17. A cart's propelled over an XY plane with an acceleration components 4 and -2. It has a constant acceleration because both of those components are constant. 4I minus 2J meters per second squared. And its initial velocity has components, well, let's say this. Trying to talk. Its initial velocity is 812, 8I plus 12J meters per second. In unit vector notation, what is the velocity of the cart when it reaches its greatest y coordinate? It's all right. So we don't know where it starts. So if we don't know where it starts, and we just need to know what is the velocity when it reaches its greatest y coordinate, we might as well just say, since nobody told us otherwise, that the initial position is 0. That's 0I plus 0j. Okay, so I want to know, I think I just need to know when it reaches its greatest y coordinate. Can I appeal back to this? Just in case you're scrubbing through this video and you didn't look at number 15. It's going to reach its greatest y coordinate when this y coordinate changes from being positive to negative. And that's going to happen after 6 seconds, right? Because this is what's happening to the velocity in the y direction. That's what acceleration is. It's the rate that it's changing at. Every second that ticks by, I'm going to subtract 2 from this. Do you know how many times you got to subtract 2 from 12 to get to 0? 6. So that's going to happen max y when time is 6. Or at time 6, you could say. So, in unit vector notation, what is the velocity when it reaches that? So, I need to do the same little game here with the x and the y like I did in 15. Excuse me. So, in the x direction, my acceleration is 4. That's going to happen for 6 seconds, and the initial velocity is 8. And we want to know, we want to know what's the velocity when this happens. So that's easy to do, actually. I mean, we can set up an equation. We can set up the VF equals AT plus a VI. But if we're really thinking about what acceleration is, it's going to do this for 6 seconds to this, right? So that means for 6 seconds, it's going to tick up by 4. That's 24. Multiply those two together, plus where you started at, that's 32. And then we can write all this stuff out, but it's the same deal. For 6 seconds, it's going to subtract 2, and of course, I mean, what's the y component of the velocity? It's going to be 0, because that's why we're here, looking at time 6. So I do believe that that's the answer right there. Intuition is good. We want to develop it. And intuition is something that you can develop, absolutely. I think that either you have good physics intuition or you don't. It can be developed over time. Moderate wind accelerates a pebble over a horizontal xy plane with a constant acceleration of 5I plus 7j meters per second squared. At time t equals 0, the velocity is 4 in the I direction, 4I meters per second. What are the magnitude and angle of its velocity when it has been displaced by 12 meters parallel to the x-axis? So that's just like a delta x of 12 meters. Not talking about the delta y, just the delta x. So let's see. It's starting... We might as well start it at the origin, right? Because they're not telling us that or anything otherwise. So let's go ahead and in the horizontal direction, its acceleration is 5. and its initial velocity, call that VI here, is 4, that is in the I direction, and delta x is 12, and we're going to need to know when that happens, right? So let's see, what equation relates to these things? I think it's our old friend. Delta x equals 1/2 at squared plus vit. So the delta x is 12 equals 1/2 a t squared plus vit. Now, I don't want to try to factor that. That's crazy. So I'm going to graph. What am I going to graph? Well, I need everything on one side, so I'm going to graph 2.5 t squared. Calculator makes an x there, but I'm thinking about t's, and then minus 12. I'd like to see where this crosses. Looks like it crosses right there, between 1 and 2. .53 to be more exact about it. Okay, so what are we trying to do here? We're trying to figure out what are the magnitude and angle of the velocity when it's been displaced. So I figured out the when of it. Now I just need to know what are the components when we get there. So there's different ways you can set up your equations and everything. I want to appeal to the intuitive side of you and say, now that we know that how long it takes for this to happen, for this 12 meters of displacement in the x direction, well, here's my initial velocity, this and no j, right? And I'm going to be doing this acceleration to it for 1.53 seconds. So that means 5 times 1.3, that's what's going to happen to this, and 7 times 1.53, that's what's going to happen to this. Basically, I'm using this VF equals AT plus VI equation, right? So there's my acceleration times time plus initial velocity in the x direction. Let me do that. 5 times 3 plus 4. Now that's 11.7 I. And then in the j direction, I have 7 times that, and plus 0. Right, 7 times that plus 0 is about 10.7 j. So that's the answer, but that's in component form, and they want magnitude and direction. So magnitude is the Pythagorized and then tangent inverse for the direction. And I'm going to say this is just like an xy plane. So I'm just going to report the direction as above the positive x-axis. Right? That's like north of east. That's the xy axis version of north of east. But I can't say north, south, east, west here. That would be wrong because there's no mention of those cardinal directions in this problem. And that's it. That was fun.